Hi folks, this is lecture 4 of I'm not sure how many for the acid-base unit, and today we are getting into polyprotic acid problems, salts, and the solubility product constant, and the common ion effect.
Another constant.
I know, yeah, it's another K, but with little different letters at the bottom.
We like K's.
Yes, so here we go. Polyprotic acids are the kind of acids that have got 2 or more protons in them. So typically, let's go to the black screen. Typically you've got acids that are like, well now, child, that is not the sort of thing that they want on their lecture, don't you? Do you think?
Pen.
There's my
There's
pen.
the pen.
Typically you've got acids like hydrochloric acid that have got 1 hydrogen on them. But sometimes you've got acids like sulfuric acid. This isn't going to be working. We're going to have to think of something else to do with this child. Just a moment. Okay, well, we got rid of that child. Here. So the hydrochloric acid has got 1 proton, so 1 H+, but the sulfuric acid, and which is a strong first proton and a weak second proton. So it's interesting when you do sulfuric acid problems that you have to treat the H's differently. And then you've also got stuff like phosphoric acid, which has got 3 weak protons. And what you've got to manage is that the first proton that comes off is weak. The second one that comes off is coming off into an equilibrium system where there's already some H+ present, and so that shifts it pretty hard back to the left, and so the second one doesn't come off nearly as much as the first one did. And then the third one can only come off of the ones that have dissociated 2 protons, which is a small number to begin with, and the equilibrium system has got even more H pluses in it, and so and you're also fighting against the fact that when you lose 2 H pluses, trying to lose the third one makes your phosphate even more charged, and so that's even less likely. So the third proton with this, generally with polyprotic acids, are even less likely to come off. So you end up with a series of Ka's where there's Ka1. Well, this is phosphoric acid. Ka1 has got a K, for phosphoric acid, your first proton has got a K of 7.5 e to the negative 3, which is pretty reasonably big, actually, for a weak acid. But the second one is 6.2 e to the negative 8, which is much less, which is like 5 exponents, so 100,000 times less of a K there. And then the Ka3 is even 5 more. So that's showing that you really do not end up with very much H+ coming off for the third one, and so that means you have a really low concentration of PO4. The problems that you see with polyprotic acid problems are generally asking you what are the concentrations of all of the different pieces. So the concentration of H3PO4, so the stuff that doesn't dissociate at all, the H2PO4, which is the one that only dissociated 1, the one that dissociated 2, or the one that dissociated all 3, and also they'll also ask for the pH, which is basically from the concentration of all of the H's added up. But what's interesting is that when you go in and do it, adding the H's up is semi-irrelevant because the second H and the third H are so small compared to the first one that it doesn't really matter. So I don't know why I don't have more room for this. Okay, so sorry to make the video jump there, but my students pointed out that when I was working on this problem in the original recording of the video, I started off using the number 5 for 5 molar phosphoric acid, and then about halfway through the first part I started using 0.5, which made for some weird answers. So here I go redoing this problem without as much craziness, let's hope. So here we go. Alright. The pH of 5 molar phosphoric acid. So first you're going to have your first dissociation of your first proton from phosphoric acid into a proton and H2PO4 1-. That's going to be in equilibrium. So you need an ice chart since this is a weak acid. And it's 5 molar, 0 and 0. You're going to lose some, you're going to gain some. And that's going to be 5 minus x, x, and x. And in the problem, it tells us that our first K, or Ka1, is 7.5 e negative 3. Our second K, A2, which we'll use for the second proton, is 6.2 e negative 8, and the Ka3 was 4.8 e to the negative 13. Yeah, okay. So to do this, we go and say x squared over 5 minus x equals our first Ka, the Ka for the first proton that comes off, which is that one, which is 7.5 e negative 3. We're going to kill our x and make sure that we go back and check to see that x is less than 5%. We'll see if I remember. You multiply by 5 and take the square root to get your x is equal to 0.194 molar. And we go back and check, and that's 0.194 over 5 times 100, and that gives you 3.88%. Now, that works, check, but it's getting close. And so I could see an instance in which with this phosphoric acid, which has a reasonably large Ka1, you might end up having to go back and do your algebra for this first part. But that's your x, which tells you the H3PO4. So we'll be able to get this one. So that's 5 minus 0.194, and that equals 4.8 when you do the sig figs, molar. So there's that guy. You've got your H plus as well, the 0.194, but it's actually going to change a little bit in a minute. But as I was saying earlier, it's not going to matter. And your H2PO4 is going to be 0.194, and then it's going to lose some. So let's go do our second proton. This species here, which you just made a little bit of, now has the opportunity to dissociate a second proton and have that system in equilibrium at the same time, leaving us with a little bit of HPO4 2 minus and adding a little bit of H plus. So that's going to be, how much H2PO4 do we have? 0.194 to begin with. And we also have 0.194 concentration of H plus present. And that concentration, according to Le Chatelier's principle, is going to kick this to the left because you've got product already present. So none of this is present in the beginning. You are going to lose some and gain some and gain some. 0.194 minus x, 0.194 plus x, and x. And so that's going to give you, with your Ka2, which is 6.2 e to the negative 8, this is the Ka for the second proton, the proton that comes off of the H2PO4 minus, and that is equal to this. No. 0.194 plus x and 0.194 minus x. And this one is actually nice and pretty because we kill our x's and we kill our 0.194s, which is awesome. We have to remember to check our x's, so let's have x is less than 5% over here and make sure that when we get x, we see that it works. So that means that x, hey, we already got x, is 6.2 e to the negative 8. We can check this and we end up with 0.000032%. I think we're good. So that's a check. That's not even close. And so that means that this x is 6.2 e negative 8, which when you have 0.194 minus 0.0000006, it's 0.194. So really your concentration of H2PO4 is 0.194, just barely less, but so far down in the sig figs that you don't care. Same deal with H plus. This is 0.194000062. That's 0.194. So that's 0.194 for H plus. And it is relevant for HPO42 minus because this is the only source of HPO42 minus. So that's going to then go do it again. We have PO4 2 minus. That is going to dissociate a proton, but really not much. Really barely any, because look how little you're starting with. You're starting with 6.2 e to the negative 8. You've got a ton of protons, none of this. I mean, how much is he going to successfully go to the right when you have this guy sitting there like a big old cranky guard? Not very much. That's correct. You're going to gain some, you're going to gain some. So 6.2 e to the negative 8 minus x, 0.194 plus x, and that's going to be x times 0.194 plus x, and 6.2 e to the negative 8 minus x equals, what's our third Ka? 4.8 e to the negative 13. And you kill your x's, which the one to check is x is less than 5% of the small guy, so we need to make sure that he's less than 5% of 6.2 e to the negative 8. He's going to be less than 5% of 0.194 if he's less than 5% of 6.2 e negative 8, that's for sure. So we do that, we do some math, we get our x. X is equal to, I love this, 1.53 e to the negative 19. It's very small. So we check, yeah, it will be fine. Look how many decimal places that is. That is, well, I didn't do that one on my paper. You lose 1 point. Alright, that's 2.5 e to the negative 10%. I think we'll be alright. That's a check. There's my flower. That means I get my point. So this is the concentration of PO43 minus. It barely affects 6.2 e negative 8. That's going to be, I love this, 6.2 e negative 8 is like 0.0000000000062. 0.0000000. It's terrible. It's 6.2 e negative 8. Because when you get down that far into the sig figs, it doesn't matter. Same deal with H+, it's still 0.194. I guess it's 0.194 0.00062000153, but it's 0.194. And our PO43 minus, the only reason that this number actually matters, since it doesn't for these, is because this is the only source of phosphate, loose phosphate in this. So that's PO43 minus, and our pH is going to be negative log of that, which is 0.71, which I know what you're thinking. You're thinking, but that's a very low pH and this is a weak acid. But this is 5 molar. 5 molar is really concentrated, and this is actually a relatively strong-ish weak acid. Because if you look at this Ka with a negative 3, I mean, he's just barely on the brink of being strong, almost strong. You can hardly call him weak. The strong acids might, in a fight, for example, call him a weakling, but really, he's kicking the tail of all of the other weak acids. All right, thanks, folks, and it'll hop back to the regular old me in a second. Problem, because it's... All right, so there's that problem. Hey, that one's not half an hour. All right, that's polyprotic acid problems. Now here's the exciting thing. The AP people have decided that they're not going to make you do one of those.
What?
I know, right?
What?
Where you have to do all the calculations for all of the thing. Like you have to run down. I will make you do at least one of them, but they're not going to have that on the exam just because I don't know, they're trying to be nice or something. What? But you do have to do qualitative reasoning about polyprotic acids, and I don't really feel like you can understand how this guy, the phosphate, ends up being affected by the presence of some of this when you get down in the calculations, and how you end up with e to the negative 19 value for this because of the presence of this thing shifting the equilibrium left, and so that kind of description would be expected, but not actually running all these calculations. So you have to understand it, but they're not going to make you do the tedious stuff on the exam.
So there you are. That's nice. And oh, I also wanted to talk about how this guy and this guy, H2PO4 minus and HPO4 2 minus, have got an interesting property. They're known as amphoteric substances because H2PO4 can accept a proton and become phosphoric acid, and it can also lose a proton and become HPO4 2 minus. So it can act as an acid by losing a proton, and it can act as a base by accepting this proton. And so that's an example of an amphoteric substance. When you see a multiple choice question asking, which of these are amphoteric substances, you look for the guy who is a family member of a polyprotic weak acid, because generally those are the ones that they're looking for. The H2PO4 can do that, and the HPO4 can do that, because he can accept this H plus and act like a base, or he can ditch this H and act like an acid. So this one is amphoteric and this one is amphoteric. Phosphate is not.
Right.
The only thing that because how's he going to dissociate a proton? He ain't got none. Yeah. So you shouldn't use he. I don't know. This species can accept an H plus and go back to the left here, so it's only a conjugate base. Okay?
Yes.
Bon. Okay, the assistant has a question, which is, when I did the pH calculation, why did I just do the 0.0576 here for the H plus concentration and not include the H's from the second and third dissociations? I could have, and let's go ahead and do that, and you'll see why I didn't do it, but I should have addressed why I didn't do it, because then it would make more sense. All right, so in your first association here, you end up with an H plus concentration of 0.0576. And then later on, your second association, you've got 0.0576 plus X. Okay, well, that's fine. That's 0.0576, 0.000062. I think that's right. -8, 1, 2, 3, 4, 5, 6, 7, 8. No, that's 9. Sorry. There's only 3 zeros. And so there's this number, 0.0576, Okay, so that's actually the number that should be here. Okay. And then plus X, so that should in fact be 0.0576, 0.0062. That's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we actually should have taken the negative log of that number. And that's down in my face, isn't it? There we go. So let's take the negative log of that number, which should be fun. Negative log of 0.0576, 1, 2, 3, 6, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 2. That's really long. And it's 1.24. I mean, it's actually 1.239577049, where previously it was 1.239577517. So there's our difference right there in the pH. That's in the 10th, 100th, 1000th, 1000th, 10,000, 100th, the millionth place. We are slightly different in the pH. So that's why I didn't include that, because I knew that in my head that the second and third H's really just don't contribute to the concentration of H+. It's important for the concentration of PO4 because it's the only source. This is the only source of PO4. But your H+ has such a big contributor up at the top that you kind of go, meh, for the other two. Yeah, okay. Now we will go back and do the other thing, which is, what is it? It's salts. You learned your solubility rules back at the beginning of the year. And
You have to remember that?
yeah, they were memorized. Do you remember that you memorized them?
Yeah.
Yeah, well, hopefully you remember them. And that's with the king and the queen and the pope and all of that funniness. And that's really useful because then when you see a salt, you can go, oh, that's not soluble. When you have learned that a salt is insoluble, what it actually means is that it's not very soluble. you've got a teensy-weensy amount that dissolves, and there's a K that tells you to what extent it dissolves. And if you have a really teeny number, like 10 to the negative 19th, that means that like one molecule ever dissolves. So that's important to know, that, you know, when you learn that something is insoluble, it means pretty dang insoluble, but not entirely insoluble. So KSP is the measure of how soluble the salt is, and the SP stands for solubility product. So this is the solubility product constant, which is how much salts dissolve. Okay. And then, actually that's here, and we'll have to come back up to this topic in a second. So KSP is the equilibrium constant for how much a not soluble salt actually does dissolve. There are a couple different problems that they're going to ask you how to do, and that's going to be able to switch from the solubility that they tell you and the KSP value. So we're going to do these couple of problems, then I'll come back up to that top thing there. Where'd they go? They're over here. All right. Copper, let's see. Copper bromide. This is cuprous, I believe. Bromide. And it's going to dissolve, and it's a solid before it dissolves. And after it dissolves is actually an equilibrium situation where that turned into calcium. It's a miracle. Copper plus and bromide minus. So this is an equilibrium situation where you've basically got a beaker with water, and you've got some kind of pathetic little cube of copper bromide in the bottom, and he's like, I can't dissolve, but you know, boop, boop, boop. Couple little dudes can come out, and they go in, they come out, they go in, they come out. There's an equilibrium of dissolving and redepositing onto the pathetic cube, and that's what this represents here. Does it have to be a cube? No, it doesn't have to be a cube. All right. So you've got this situation here, and you can make an ice chart for it. And this is this is a solid, and so it doesn't end up showing up in your equilibrium expression. And so they don't really tell you how much there is. It doesn't matter how much there is. You can put in a big cube, you can put in a small cube, you can put in a whole lot, you can put in a little. It's going to dissolve depending on it. It's going to dissolve to the same concentration as long as the temperature is the same. So we don't really care how much is in there. You are going to lose a little bit. I kind of put that in parentheses because you need to remember it's not super relevant to the equilibrium expression, but you do lose a little bit. And so at equilibrium, you have lost a little bit of your chunk of copper bromide, but that doesn't go in. You don't have any of this to start with, and when you lose a little bit of this, you gain 1 mole of this every time you lose a mole of this, and you gain 1 mole of this every time you lose a mole of this. So you have X and X, and so your KSP is equal to your concentration of copper ions times your concentration of bromine ions, and that's it. There's no bottom. So these are actually kind of prettier because there's no dividing, because the reactants are solid lumps and they don't show up. So this is a solubility product in the sense of, hey, you multiply and that's it. It's the multiplying solubilityness. That's the SP. So the solubility is 2.2 E negative 4 moles per liter. That's pretty small. And so if you think about copper bromide, this is generally considered to be an insoluble salt, but a teeny weeny bit does dissolve. Your solubility, this number is your X. That's the molar, that's the amount of it that has gone into solution. So that's helpful. They basically have given you your X equals that. And so to calculate its KSP value, you just go, oh, fine, X squared. So 2e to the negative 4th squared is 4e to the negative 8. And here's your head math, because when you're multiplying, you multiply the numbers to get the 4, and you add the exponents. So 4e to the negative 8 is your KSP value. That's it. Sometimes they'll give you the KSP and make you figure out your X. That's sort of easy when all you have is a top, actually. So let's see if we can do one of those.
What does that mean?
What does that mean?
What does that number mean? My KSP 4e to the negative 8.
It means that it's really more useful to look into when you have like a list and you can compare things. And you can say, hey, that one dissolves more than that one does. They're both considered insoluble, but that one's really, really insoluble. He's got, 1e to the negative 20 for his KSP. Good heavens, you say to yourself. So it's sort of helpful in a comparison list, or if you are looking at, like, you have some insoluble salt with arsenic in it and you want to know how poisonous the water is. So
Okay,
it ends up being relevant when you care how much has dissolved in the water.
Okay.
But this is just sort of getting you used to doing the math, switching back and forth between the KSP and the solubility, which ends up being your X. It's really all the same math as what we've been doing before without a bottom, so it's easier.
Says this much dissolves in 1
liter.
Okay.
Yep. All right. So copper iodate, which is this guy, copper iodate. It's an interesting ion that we're not super used to, but they told us about it, and told us what the formula was. That was nice. Copper and iodate. That's copper 2 iodate. Boom, 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 boom. So that's iodate with a single charge, and there's going to be 2 of them, by the way. That's important, because that 2 is going to show up. If you forget that 2, you're just wrong. So it's just gonna mess up your math totally. So you've got some amount of this, you're gonna lose some, and you're gonna end up with some having been lost. When you lose a mole of this, you gain a mole of this, and you gain 2 moles of this, right?
What's my charge on the copper?
Yeah, the copper is 2+. You're right, it should be an ion. All right, because it's in solution, it's not going to be dissolved if it's the metal. All right, the KSP is this. So your KSP is equal to your copper times your iodate squared. When you're doing these, it's really important to write this out before you go straight to the algebra version, because you're going to forget that too if you go straight to the algebra version, because it shows up twice. You'll see in a second. It's 1.4 e to the negative 7 and x, and 2x goes in there squared. That's a 2 sourced from here that shows up twice in the algebra. So you're gonna think, if you go straight to your x stuff, you're gonna go, oh, I used my 2, it shows up more than once. Okay,
That's tricky.
so do this, it's good for you. And then you end up having 4x squared x cubed. So 4x cubed is 1.4 e to the negative 7. You divide by 4, and then you cube root, which your calculator can do. There's a little spot for it on the math button, or you can raise it to the 1/3 power. That's the same as taking the cube root, and it's easier to type. So what did I get? I don't know. So your x is 0.00327, and that's your solubility, moles per liter. Bam. Okay?
Why is it squared? Why is the iodate squared?
Because the way that you form these expressions is the concentration of the products to the power of its moles.
There we go.
So it's copper to the first power and iodate to the second power. And then you fill in iodate is going to be a 2x value.
There we go.
So that's why that 2 shows up twice.
Yep. Thank you.
Okay. And this one is going to come up later when we get to the common ion effect. So we'll come back to that. So that's how you do KSP.
Okay.
It's not bad.
No.
You end up with kind of nice stuff like 4x cubed, where it's pretty easy to solve for x. All right. Now, Acidic and basic salts. Sodium chloride, salt solution. It's neutral. It's pH 7. Well, of course, it's a salt. All salts are neutral.
Uh-oh.
No.
Uh-oh.
Not all salts are neutral because, sodium, if you had a reaction to create sodium chloride in a neutralization reaction, what reaction do you suppose that would be? Can you come up with one imaginarily? If you were imagining a neutralization reaction that made sodium hydroxide as a product and water too. Not sodium hydroxide, no, sodium chloride.
There we go.
I gave it away. Sodium chloride as a product and H2O as another product. What were the two things that neutralized?
Hydrochloric acid.
Hydrochloric acid and
Plus sodium hydroxide.
sodium hydroxide. All right. What kind of acid is that?
Strong acid.
What kind of base is that?
Strong base.
So that's strong, and that's strong, and this ends up being neutral. Interesting. All right. And then our other thing that we have to consider is sodium acetate. If you had a neutralization reaction that resulted in sodium acetate and water, what was it that you neutralized?
You did acetic acid, C2H3O2
And
sodium hydroxide.
Sodium hydroxide. Okay. What kind of acid is this?
It's a weak acid.
Weak acid. And what kind of base is this?
Strong base.
Strong base. This contains the acetate ion, which is the what of this?
It's the conjugate base.
It's the conjugate base of this weak acid, right?
Right.
The conjugate base of a weak acid has a Kb. When it's by itself in solution, it's acting like a conjugate base. It is a conjugate base, I believe. So when you have strongs and strongs, you end up with neutrals. When you have a weak and you end up with a salt solution containing its conjugate,
Base.
then it changes the pH. So
Tricky.
yeah, strong things, salts that come from strong things do not affect pH. Salts that come from weak things do.
Okay.
So this is a weak acid, this is a weak base. And so that explains why sodium acetate solution is basic. It's because the acetate is the conjugate base of a weak acid, so it's got a Kb, it's basic. So our little blanks here, salts composed of ions from strong acids and bases don't affect pH. But salts composed of ions from weak acids and bases are their conjugate bases or acids. One of the types of questions that is really popular in multiple choice for this particular topic is, here's a salt, is its solution acidic or basic? So you have to look at the two ions and go, okay, that's from a strong thing, doesn't matter. Ooh, that's from a weak thing, does matter. So let's go and do that a few times. All right, sodium fluoride. Sodium is from sodium hydroxide. Fluoride is from hydrofluoric acid. Sodium hydroxide is strong or weak?
Strong.
So he's irrelevant. Hydrofluoric acid is
A weak acid.
a weak acid. A weak acid gives you fluoride, which is the conjugate base of a weak acid, so it's going to make this
Slightly basic.
basic. Let's see if I can get my pen to work.
No.
No, it doesn't love me. All right.
Like you.
So this one is basic. All right, KNO3. K is from what?
KOH.
KOH, which is
Strong.
strong, so K is irrelevant. NO3 is nitrate, which is from
Nitric acid.
nitric acid, which is
Strong.
strong. Both irrelevant, this one's neutral.
Yay.
Okay? Ammonium is from what?
Ammonia.
Ammonia, which is
Weak.
a weak
Base.
base. So ammonium is a
Acid.
weak acid. So that's going to make it slightly acidic. Chloride is from
Polyhydrochloric acid.
hydrochloric acid, which is
Strong.
so is
So it's irrelevant.
so it's irrelevant.
Okay.
There we go. So this one is going to be
A weak acid.
a weak acid. That's how you do these. I will leave this one, and this one to the reader. This is interesting because you've got NH4, which is ammonium, which is slightly
basic.
Well, ammonia is basic, ammonium is
Slightly acidic.
And fluoride, which is slightly basic. So a slightly acidic with a slightly basic. But well, does that end up being perfectly neutral?
Don't know.
It matters what their K's were.
Aha.
So you've got to figure out what the Ka is for ammonium and what the Kb is for fluoride. And they helpfully usually provide the Kb for its conjugate, and so you have to switch it.
Okay.
So you go and you switch this Kb for ammonia to the Ka, and you go and switch this Ka for hydrofluoric acid to the Kb for fluoride.
And how do I do that again?
And the way that you do that is this, Ka times Kb equals K water. And the value for Kw is
1e to the negative 14.
And so Ka, so let's do the first one. I'll do the first one, okay? Fine, I'll do the first one. We want our Ka for that guy, so our Kb was 1.8 e to the negative 5. Which, here's the one that I mentioned that comes up all the time. So the, yeah, well, this is actually ammonium. It comes up.
That's the other one.
Yeah. So 1.8 e negative 5. So your Ka is 5.56 e to the negative 10. And the other one ends up being the Kb for fluoride ends up being 1.38 e to the negative 11. This one is bigger, so it's more relevant. So it ends up being slightly acidic. Okay? Yay! So those are harder when you've got two, and you'd have to compare their relevant Kas and Kbs. But in general, you can just go strong, weak. Hey, there we go. All right. And now the common ion effect. Common ion effect. If there is some nitrate already present when you've got HNO2, do I have this on the problem? No. So let's do that. If you had a beaker of stuff and there was some NO2 dissolved in it, maybe you dissolved sodium nitrite in there. So you've got little sodiums in there. Sodiums aren't really relevant. You've got some nitrite already present. If you go and try and dissolve nitrous acid in there, this is what happens to the equilibrium. You've got, yeah, you see,
yeah,
you've got like say 0.1 molar this, and you've got none of this, and you've got 0.1 molar this, minus x plus x plus x. It ends up screwing it up because this is called the common ion effect, and it's an application of the Le Chatelier's principle, which says I've already got product. It's not going to let you shift as much to the right as you normally would. So this being present already, because they share a common ion, the ion that they have in common is nitrite. It's going to prevent the nitrous acid from dissociating as much as it wants to. The K is still in effect, but you've got this 0.1 in the way. So there you go, there's that. And let's do the problem that they gave us, if I can find it. Where is it? Ooh, it's over here. So calculate the solubility of calcium fluoride in a 0.025 molar solution of sodium fluoride. To do this one, let's go ahead and calculate it as if it were normal. So calcium fluoride gives you, and that's a solid, and this is a sort of a KSP sort of thing to be dealing with calcium and fluoride if this were in pure water, you would have,
negligible, right?
yeah, you have, whatever, you have a chunk of this. You have 0 and 0, and you lose some of this. You gain some, you gain twice as much. And x and 2x. And your KSP is calcium and fluoride squared. And you end up with 4e to the negative 11 equals x times 2x squared. So you end up with 4x cubed is 4e to the negative 11. You divide by 4, so you get 1e to the negative 11 is x cubed. And you cube root these, and you end up with x equals, here's the one I did for water. There it is. 3.42 e to the negative 4. So that's your solubility in just regular old water. So let's compare that to when we do it when there is some fluoride already present. Which, how much? 0.025. So let's do that again. Calcium fluoride, solid. Whatever, minus some, 0. And if you had some fluoride in there already from sodium fluoride, if you had some fluoride in there already, then you're going to gain some calcium. You're going to gain twice as much fluoride, and so you've got x and 0.025 plus 2x, and so you have,
Oh, it's trickier.
yeah, that one's not quite as easy to do. 4e to the negative 11 equals x times 0.025 plus 2x squared, which we're going to go ahead and discard that x and hope that it works, because the negative 11 will be nice and pretty. Let's do this. So x ends up being, I did all the math, 6.4 e to the negative 8 molar, and we got to go check that. And that gives us 0.0005%. We're good. So comparing these two, we've got 3.2 e to the negative 4 solubility if it was in pure water, and 6.4 e to the negative 8 solubility if you mess with it and put some fluoride in already. That's a big difference. That's way less, and so you can prevent dissociation of a salt by putting in one of its ions, which might be relevant if you wanted to prevent something from dissociating if, say, the metal that it had in it was toxic, something like that. So there you are. The common ion effect is from Le Chatelier's principle, and you can kind of reason it out, and you can also do the math and prove that, hey, pure water, you got more solubility. If you mess with it and put in an ion that they have in common, then it's much less. All right, that is long enough, and I will do, will I? No, this isn't that long. Is this that long?
Doesn't look bad.
It doesn't look that long. All right, we'll go do that problem. Where is that problem? It's over here. All right, calculate the pH of the following solutions and then think about what it means. All right, propanoic acid, prop, meth, eth, prop, C3, right? So this is propanoic acid. This is an organic acid, this guy. Remember this guy?
Yes.
Yes, this is the carboxylic acid, an organic acid, so of course it is weak. Calculate the pH. Okay, that's easy. You just got to do this. I've done this like 65 times. It's not actually 65. Shh.
Probably close though.
I know, right? And then propanoate is the name of the ion, which is pretty nice. 0.100 minus x plus x plus x. 0.1 minus x, x and x. x squared over 0.1 minus x equals that guy 3e negative 5. Kill the x. X is less than 5%. You're going so fast. I know, you've done these. Don't worry. So this is times 0.1. Oh, this one you can do in your head, I think. I don't want to do it in my head. Shh. Over 0.1 times 100. So times 0.1 is going to be 1.3 e to the negative 6 equals x. Oh no, you can't do this in there. I thought that was a 6. You can fiddle with, if it was 1.6, you could make it 16, and then you can do a square root, but no, you can't do it in your head. Boo. And you end up with x equaling, what do you end up with x equaling? 0.00114. And that's your H concentration. And so to get your pH, you take the negative log of that doohickey. And you end up with a pH of, what should it be? Some, like, what sort of number should we be getting? Yeah, some sort of kind of vaguely reasonable pH. Oh, you're amazing. 2.94. Haha, you're great. So there is the pH of propanoic acid. Okay, you should know how to do these by now.
Do your X.
Do my X. You should know how to do these by now, and I should stop forgetting to do that.
Get so excited.
I know, I do. I want to keep going. It's 1.1%. We're fine.
Okay, so we're still good.
We're good. We don't have to go back. Yeah, it was pretty serious that one time. Okay, so we've got this next part, which is find the pH of this solution, which is 0.1 molar sodium propanoate. And the thing to think about is propanoate in solution. And this is related to the pH of salts. If you've got this salt, sodium propanoate, sodium is from
Sodium hydroxide.
sodium hydroxide, and propanoate is from
Propanoic acid.
propanoic acid. So do either of these affect the pH?
The propanoate does.
The propanoate does. It is the conjugate base
Of weak acid.
of a weak acid. And so it's going to affect the pH. What's it going to make the pH like?
Slightly basic.
Slightly basic. So a prediction and a guess is?
8.
8. Okay. So now here's the thing that's important to remember, which I forgot to remember, which is weak bases attack water. And when they attack water, they reform the acid form and leave behind hydroxide. And so you've got this as your equilibrium. This is your equilibrium, and we've got 0.1 molar here. We don't care about water. We don't have any of this. We don't have any of this. We lose some. We gain some. And you end up with Kb,
Ooh.
because this is a base,
Ooh.
equals x squared over 0.1 minus x. And our Kb is from this Ka. We cannot just straight up use this Ka. You have to flip it. So that's going to be 1e negative 14 divided by that 1.3 e negative 6, which I think is what that number was, right? Yeah. Equals x squared over 0.1. We killed the x. Is x less than 5%? I should hope so. Am I going to remember to go back and do it? Only if the assistant tells me to.
I'm so good.
So you do that, you get your x. Your x is...
Can they have an assistant on the test?
No, they do not get an assistant on the test. Your x is 8.77 e to the negative 6. And you take the negative log of that number. And what you get is some number, 5.06. And what is that number?
That's my POH.
That is your POH, because that's your x. So your POH gives you your pH by subtract, and you get 8.94. Hey, that's not bad. 9 would have been better.
9 would have been
Okay,
better.
a mixture.
Did you check your
I didn't check my x. I never check my x. Why should I check my x? Checking my x is for chumps. And what do we get? We get 0.008%. Check my x. I always forget to check my x. It's going to be great when my kids forget to check their x's. They'll be like, it's because you told us to. It's not. All right, a mixture. Now this is very important, and this is like leading up to the future.
There's more of this?
There's more. I know.
It gets more complicated?
There's a whole nother page.
Oh.
All right, a mixture that has got propanoic acid and sodium propanoate.
It's kind of fun.
I know. Isn't this wonderful?
You guys probably don't believe me, but it's kind of fun.
H5O. How many O's? 3, 2.
2.
Yield some acid H's and some basic dudes. And ice. It's 0.1 molar in propanoic acid. We don't have any of this yet, but we put in some sodium propanoate as well. So now we have put in on purpose the acid and its conjugate base. Plus X, 0.1. Do you see how pretty this is going to be? It's going to be pretty. And since we're doing the acid here, we can use that Ka. Kill the X's. X is less than 5%. All right, let's see if I remember this one. You think I'm going to remember it?
Maybe.
I don't think I'm going to. The 0.1s cancel. Your X is equal to 1.3 e negative 6.
Oh, that's very pretty.
You know, isn't that pretty? And I'm going to check it.
Ha! She remembered!
And you end up with the percentage being 1.3 e to the negative 4%. Will be fine.
Good there. Oops.
I'm gonna undo that. Don't click the button on the pen. Okay, and negative log of 1.3 e to the negative 6 gives me a pH of 4.89. All right.
It's different.
It is different. It's nice and in between this, the 9, and the 2.94. And this sort of mixture where you put in an acid and its conjugate base on purpose is going to be very useful in buffers.
Dun dun dun.
The next lecture is about buffers, and that's all I got to say. Good night.